Hi everyone, it's Zhenxi here from Group 26, and today we'll be presenting our project on Abalone age prediction using AI. Our team members include me, Cheng Zhenxi, as team leader, Tan Qihan, Aaron On, Li Waitak, and Wang Zhongjie. You can also check our project on GitHub, and the YouTube links is provided below. Let's move to introduction. Abalone age prediction is crucial for marine biology and aquaculture. Traditionally, it involves counting shell rings, a tedious and invasive method. AI and machine learning offer a more efficient approach by analyzing physical attributes like length, diameter, and weight. Our project explored three models: linear regression, XGBoost, and the MLP regressor to predict abalone age with greater accuracy. Let's move to literature review. Previous research has shown that machine learning is effective for abalone age prediction. Studies have tested artificial neural networks, regression models, and convolutional neural networks, and ensemble methods. And notably, we found that XGBoost has been found to outperform traditional models by reducing prediction errors. And our study will build on these findings to compare our three models, which is linear regression, XGBoost, and MLP regression, and optimize their performance. Now I will be handing the presentation to Qihan.
Hello everyone, my name is Tan Xihan. Today I will talk about slides 5 and 6. First, in our literature review, we analyzed different machine learning models, including artificial neural networks (ANS), regression-based neural networks (RNS), convolutional neural networks (CNS), and ensemble methods. This research shows that BPFAN achieved 88% accuracy, CNS achieved 69.09% accuracy, and Chubby Boost combined with Sharp reduced MAE by 82.5%. ANS are accurate but computationally intensive. RNS are precise but sensitive to outliers. CNS capture spatial relationships but require large database sets. Data sets. Chubby Boost improves interpretability but risks overfitting. Next, in data preprocessing, we applied label encoding to convert category feature into numerical values. We also used feature scaling to standardize numerical attributes, ensuring balanced input for the model. Finally, we speed the dataset into 60% training and 40% testing to evaluate performance effectively.
This is our model design. We have three of them. The first one is a linear regression that establishes a simple linear relationship between features and target. And number two, we have XGBoost. It handles the nonlinear relationships, feature selection, and it's optimized using grid search CV. And our third one will be our NLP regressor that's optimized using the grid search CV. So our next slide will be our linear regression's performance. It has a MAE of 1.628, MSE 4.85, and our R-square score is 0.5. And the scatter plot compares the actual abalone age to what the linear model predicts. Points deviate more noticeably from the diagonal line than in the XGBoost or MLP plots, reflecting larger errors and more systematic bias. The cluster points at higher actual ages beyond 15 shows a tendency for underestimations, which aligns with the lower R square and higher MAE, MSE for linear regressions.
Hi everyone, so now I will talk about second model, the XGBoost regressor. So XGBoost regressor is an advanced boosting algorithm that builds digital trees sequentially to improve accuracy. So on the left side of the graph, the blue curve shows training errors and the orange curve represent the validation errors. The validation errors flatten around 150 boosting rounds, meaning additional trees provide diminishing returns. So on the right side of the graph is the predicted versus actual age. Many predictions align with a red diagonal line, but some scattered remains, indicating minor inaccuracy. So the performance of these models, the mean absolute errors is 1.56 years deviations from actual age, and the mean square errors is 4.71, indicating occasional larger errors. The R-square scores is 52.4% variance explained, improving over linear regressions. The key takeaway is XGBoost improved predictions but slightly more scattered than uh, linear regressions. Sorry. So the next slide will be MLP regressor. MLP uses neural network to learn complex patterns, improving predictive accuracy. So the left side of the graph is the loss curve. The loss dropped sharply in the first 10 to 20 iterations, showing fast learning and convergence. And the right side is a predicted versus actual age. The prediction cluster closest to the red diagonal line, indicating high accuracy than XGBoost. So the performance of this model, the mean absolute errors is 1.549 years deviations, the lowest amongst our models. And then the mean square errors is 4.31, reducing large errors. The R-square scores is 56.4%, outperforming XGBoost and linear regression. So the key takeaway, MLP regressor is the best performance, minimizing prediction errors and generalizing well. So I'll pass the next slide to my team member. He will explain the result and the conclusions.
Now, let's move on to the model design to predict the age of Abalone. We explored three machine learning models: linear regression, XGBoost, and MLP regressor. Each model has different strengths and weaknesses, and we aim to find the most effective one. So for linear regression, first we use linear regression as our baseline model. It assumes a direct relationship between features like shell length and age. While simple and interpretable, it struggles with capturing complex patterns in the data. Next, for XGBoost, which is gradient boosting regressor, we applied XGBoost, a powerful gradient boosting model. XGBoost builds decision trees sequentially, where each tree corrects errors from the previous one. This allows to handle non-linear relationship better than linear regression. MLP regressor, which is a neural network. We've implemented an MLP regressor, which is a type of neural network. This model consists of multiple hidden layers that learn complex relationship in the data. Now that we have designed our models, let's see how they perform. To evaluate our models, we use three key performance metrics: mean absolute error (MAE), mean squared error (MSE), and R-square score. MAE measures the average difference between predicted and actual age. Lower MAE means better accuracy. MSE is similar to MAE, but penalizes larger errors more heavily. R-square score measures how well the model explains the variance in age. Higher R-square means better performance. Let's look at the results of our three models. Linear regression has the highest error, with an MAE of 1.63 years and an R-square score of 0.509. This means it doesn't capture complex patterns well. XGBoost. It improves accuracy with an MAE of 1.56 years and R-square of 0.524. It performs better than linear regression, but still has some scatter in predictions. MLP regressor achieves the best performance with an MAE of 1.49 years and an R-square of 0.564. This suggests that neural networks can capture non-linear patterns in the data more effectively. So from the insights from the visualizations, looking at the scatter plots, we use that linear regression underestimates the age of older abalones, making its prediction less reliable. XGBoost reduces error but still has some variation. MLP predictions are more closely clustered around the true values, making it the most accurate model. Now that we have seen the results, let's conclude with key takeaway and future improvements. To summarize, we compared three models for Abalone age prediction. Each has its advantages, but our results highlight the effectiveness of neural networks. Linear regression serves a simple baseline but lacks accuracy. XGBoost improves predictions by capturing some non-linear relationships. MLP outperforms both models, achieving the lowest error and highest accuracy. So for future enhancement, although MLP performed the best, we can further improve our model with this enhancement. Feature engineering. Adding more relevant attributes could improve accuracy. Exploring different architectures for the MLP may yield better results. Combining multiple models might enhance predictive performance. In conclusion, while simple models like linear regressions are easy to implement, more complex approaches like XGBoost and MLP significantly improve accuracy. With further optimizations, we can make Abalone age prediction even more reliable. That brings us to the end of our presentation. Thank you for the attention.